Testing, can you hear me? Testing, can you hear me? I'm testing my mic. This video isn't public yet. Okay, this video is public now, so I hope everyone can hear me. So I'm going to be studying calculus again. Last time I learned about Green's theorem. By the end of it, I did get quite confused, but I did get the general idea. Uh, Let me just go back. Hello. All right. So Green's theorem said, yeah, that if you want to find this circulation, this is equal to the double area, the same region. Like if you want to find the vector line integral of this curve, of a closed curve, you have to find the area of the region it covers. Well, like on the we need to double integrate on the region it covers of px minus qx minus py, x minus py. Also, f is defined like this. Sorry, like this. F is a vector field. Also, there was another one. Yeah, then they had the flux form as well. Where if you want, instead of tangent, we are using the unit normal vector. And in order to find this vector integral, use double integral in this region with px plus qy. That were the two main things they taught us. Next topic seems to be about divergence and curl. I don't know what this is. Divergence is an operation on a vector field that tells us how the field behaves towards or away from a point. Locally, the divergence of a vector field f in r square or r cube at a particular point p is a measure of the outflowingness of the vector field at p. If f represents the velocity of a fluid, then divergence of p measures the net rate of change with respect to time of the amount of fluid flowing away from p. The tendency of the fluid to flow out of p. Particularly, if the amount of fluid flowing into p is the same as the amount flowing out, then the divergence at p is zero. Okay, I have no clue. If f is this, if f, capital F is a vector field in R cube, and px Qy, and Rz all exist, then the divergence of f is defined by divergence of f is Px, Ky, Rz. Hold on. So vector field, let's say I have two-dimensional graph here. Two-dimensional graph here. And then a vector field would define a bunch of vectors. Yeah. And then like this vector field is P Q. So what they're saying is that divergence of f is equal to derivative of the first derivative with the of the x component with respect to x plus derivative of the y component with respect to y. So I guess it's calculating the change in the vector field at point P. So at this point, for example, the vector field is pointing in this direction, and then divergence would calculate the change in this, I think. Now that the divergence of a vector field is not a vector field but a scalar function. Um, it's a scalar function. So it's the sum of the change in the three directions, right? Uh, in terms of gradient operator, divergence can be written symbolically as the dot product. Hold on, I'm seeing that the first time gradient operator. If f is defined, never mind. I'm seeing this the first time gradient operator. So divergence of f is the gradient operator dot f. This is merely a helpful notation because the dot product of a vector of operators, a vector of functions, is not meaningfully defined given our current definition of dot product. I mean, this isn't really a vector. What does this even mean? Gradient of what with respect to x? This is just a notation thing, right? If f is pq is a vector field in R square, then the divergence is defined like this. To illustrate this point, consider two vector fields in figure 6.5. So figure 6.5, we have this vector field and this vector field. At any particular point, the amount flowing in is the same as the amount flowing out. So at every point, the outflowingness of the field is zero. Therefore, we expect the divergence of both fields to be zero. This is indeed the case. So how is this defined? A is defined as 1, 2. So the vector is 1, 2 everywhere. And the divergence is 0. And in this part also divergence is 0. But I don't understand the definition. What do they mean by outflowingness? Like the amount flowing in is the same as the amount flowing out. By contrast, consider radial vector field minus x minus y. At any given point, more fluid is flowing in than flowing out, and therefore the outgoingness is the field is negative. We expect the divergence of this field to be negative, and this is indeed the case. What did they mean by this? More fluid is flowing in than is flowing out. Measure of outflowingness of the vector field. If F represents the velocity of a fluid, then the divergence of F at P measures the net rate of change with respect to time of the amount of fluid flowing away from P. To get a global sense of what divergence is telling us, suppose that a vector field in R square represents the velocity of a fluid. Imagine taking an elastic circle with a shape that can be changed by the vector field and dropping it into the fluid. The circle maintains its exact area as it flows through the fluid, then the divergence is zero. Okay, so if a fluid is going like this in two dimension and I throw a rubber band, it won't change its shape, right? Even in here, but it would move in that direction, right? And in this, it will be rotating. If I drop a rubber band at center zero, like at the center at the origin, I drop a round rubber band, it would be going, it will be rotating around the origin, right? Because that's how the fluid is flowing. What about here? Imagine taking an elastic circle, dropping it into a fluid. If the circle maintains its exact area as it flows through the fluid, then the divergence is zero. This would occur for both vector fields. On the other hand, if the circle's shape is distorted so that its area shrinks or expands, then the divergence is not zero. Imagine dropping such an elastic circle into the radial vector in 6.51 so that the center of the circle lands at 0.33. At 0.33 over here would be the center of the circle. Yeah, if the circle is over here, the vector field is stronger at this point than at this point, right? The circle would flow towards the origin, and as it did, so the front of the circle would travel more slowly than the back, causing the circle to shrunk, lose area. This is how you can see a negative divergence. If F is this, then the divergence of F, then find the divergence of F at 0, 2, and 1. Example 6.48. So what did they say? F of xyz is e to the power of x, yz, yz square minus yz square. E to the power of x, yz minus yz square. And then p is at 0 to negative 1. 0 to negative 1. So the divergence of f, or I think this is a better notation. Uh, yeah, it's a sum, right? So e to the power of x plus derivate this with respect to y, derivate this with respect to z, and then I have to substitute in the values x, z, negative 2, 2, negative 1. E to the power of 0 is 1 plus 4, 4. One application for divergence occurs in physics when working with magnetic fields. A magnetic field is a vector field that models the influence of electric currents and magnetic material. Physicists use divergence in Gauss's law for magnetism, which states that if B is a magnetic field, then the divergence of B is zero. In other words, the divergence of the magnetic field is zero. Determine whether a field is magnetic. Is it possible for f x y x square y minus xy squared to be a magnetic field? Right. Let's see. Um 6.49 x square y minus x y square y minus xy square x square y. The divergence of f is you derivate this with respect to x, you derivate this with respect to y. Uh, so no, right? Because the divergence is 1. If f p q is a source-free continuous vector field, a differentiable component, then the divergence is 0. The converse of divergence of a source field vector field is true on simply connected regions, but the proof is too technical to include here. Thus, we have the following theorem which can test whether a vector field in R square is source free. Divergence test for a source free vector fields. Let FPQ be a continuous vector field with differentiable component functions with a domain that is simply connected. The divergence of f is equal to 0 if and only if f is source free. So determining whether a field is source free, you just have to check whether the divergence is 0, right? 6.5 x square y 5 minus xy square plus derivative with respect to y. This becomes 0, this becomes 2xy, which is 0. So it is source free, right? So the condition for being source free is that the divergence is 0. The current and the flux form of Green's theorem says that f dot n is equal to this. A C is a simply closed curve and D is the region enclosed by C. Since Px plus Qy is equal to divergence of f, Green's theorem is sometimes written as this. Okay. Therefore, green theorems can be written in terms of divergence. If we think about divergence as a derivative of sorts, then green theorem says that the derivative of f on a region can be translated into a line integral of f along the boundary of the region. This is analogous to the fundamental theorem of calculus, in which the derivative of a function on a line segment can be translated into a statement about f on the boundary of AB. Using divergence, we can see that Green's theorem is a higher dimensional that Green's theorem is a high dimensional analog of a fundamental theorem of calculus. We can use all of what we learned in the application of divergence. Let V be a vector field modeling the velocity of a fluid. Since the divergence of V at a point P measures the outflowingness of the fluid at P, if divergence is more than zero, implies more fluid is flowing out of P than flowing in. Similarly, divergence less than zero implies uh, more fluid is flowing into P than flowing out. Divergence of P is equal to zero implies the same amount of fluid is flowing in as flowing out. So fluid flowing in, flowing out. I need to understand that. Let's say we have an elastic band. Suppose all the vector fields, suppose this vector field points in that direction. All of them point in that the direction is the same, but the gradient is different. Suppose you draw like this elastic thingy over here at this point, and suppose the divergence is same everywhere. The band would be flowing in that direction, but the thing is, um, if this band is like while flowing over there, it's like increasing in size over here, then there's more fluid flowing out than flowing in, right? If there's more fluid flowing out, then divergence is more than zero. Otherwise, as the rubber band is going in, there's more fluid going in, and this is not increasing a lot. And there's more fluid flowing in than flowing out. The divergence is less than zero. But the thing is, how is that possible? Shouldn't matter remain the same? Suppose Vxy is this, for y is more than zero, mod is the flow of a fluid. Is more fluid flowing into 0.14 than flowing out? I still can't wrap around it. How can like shouldn't the amount of fluid always be same? So shouldn't it be like equal amount going in and coming out? How can you have more going in or more going out? Example 6.55. Vxy. So this vector field minus xy is defined like this only for y is more than 0. And they're talking about point P 1 4 minus xy and 1 4. So divergence of P is derivate this with respect to x, derivate this with respect to y is 1. And they said y is more than 1, right? So minus y is less than, so sorry, more than 0. So minus y is less than 0. This is less than 1. So x is 1, y is 4. This is negative 4. We have minus 3. So the divergence is negative. More fluid flowing in than flowing out. Because the change in vector field is not increasing. The second operation on a vector field that we will examine is the curl, which measures the extent of rotation of the field about a point. Suppose that F represents the velocity field of a fluid, then the curl of F at a point P is a vector that measures the tendency of a particle near P to rotate about the axis that points in the direction of this vector. The magnitude of the curl vector at P measures how quickly the particle rotates around this axis. In other words, the curl at a point is a measure of the vector field's spin at that point. To see what curl is measuring globally, imagine dropping a leaf into fluid. As the leaf moves along with the fluid flow, the curl measures the tendency of the leaf to rotate. If the curl is 0, the leaf doesn't rotate as it moves through the fluid. So, okay, they all exist. Then the curl of F is defined like this. Curl of F, oh my god, Ry minus Qc, Pc minus Rx, and Qx minus Py. Okay, I think this is easier. So this minus this. And then for j, it's this minus this. For k, it's this minus this. How do you even prove such a thing? If fpq is a vector field in R squared, then the curl of f by definition is qx minus pyk. Hold on a minute. This curl is in 3 dimensions, ijk, and is defined in R cube. This is only in k. So this minus this. Oh, because yeah, these two would be 0 maybe. So 0 minus this. There is no change in z, right? 0 0 0 0. Yeah. Example 6.52. P Q R X square C e to the power of y plus xc xyz. Um, is there some notation for curl or do I just write curl? Determine P Q R X square C x to the power of yx. And then this. Um, let's see. So for I, we have these two. So this derivative with y, derivative with respect to y, we have x z minus it with this derivative with respect to z. We have just x. Yeah, write it as a vector. So for j, we have these two y z x square. And for k, we have just z minus 0. Sorry, wait, for k, we have, yeah, but it's a derivative with respect to x. Um, Wait, is this it? This is the answer, right? For the maiden one, I have, so for j, we have this with respect to this. Get y, z, this is c. Y, z minus x squared. But yeah, I forget the middle one turns negative. Finding the curl of a two-dimensional. Okay, let's just get that. Note that if f is equal to pk is a vector field in a plane, then curl fk is equal to qx minus py k dot k. which is qx minus py. Therefore, the circulation form of Green's theorem is sometimes written as this is equal to the area of the curl f dot y dot k, where C is a simple closed curve and D is the region enclosed by C. Therefore, the circulation form of Green's theorem can be written in terms of the curl. If we think of curl as the derivative of sorts, then Green's theorem says that the derivative of f on a region can be translated into a line integral of f along the boundary of the region. This is analogous to the fundamental theorem of calculus. We can now use what we have learned about curl to show that gravitational fields have no spin. Suppose there is an object at an origin with mass m at the origin and an object with mass m2. We call it the gravitational force that object 1 exerts on object 2 is given by the field. We have this. It's r cube. And then all of this would be equal to 0. Now that we understand the basic concept of divergence and curl, we can discuss their properties and establish relationships between them and conservative vector fields. If f is a vector field in R cube, the curl of f is also a vector field in R cube. Therefore, we can take the divergence of a curl. The next theorem says that the result is always 0. This result is useful because it gives us a way to show that some vector fields are not curl of any other field. To give the result a physical interpretation, recall that divergence of a vector field at point P measures the tendency of the corresponding fluid to flow out of P. Since divergence of curl is equal to 0, the net rate of flow of the vector field curl B at any point is 0. Taking the curl of vector field F eliminates whatever divergence was present in F. The divergence of curl, this is equal to 0. In the next two theorems, we show that if f is a conservative vector field, then its curl is 0. And if the domain of f is simply connected, then the conserve is also true. This gives us another way to test whether a vector field is conservative. Curl of a conservative vector field, if f is conservative, then the curl is 0. Since conservative vector fields satisfy the cross partials property, all cross partials of f are equal. Therefore, this should be equal to 0. Since the conservative vector field is the gradient of a scalar function, previous theorem says that curl this is equal to 0 for any scalar function f. In terms of a curl notation, gradient cross gradient of f is equal to 0. This equation makes sense because the cross product of a vector with itself is always the 0 vector. Sometimes equation curl gradient times gradient is simplified as gradient times. If curl is 0, then we have that this is equal to this is equal to this, and this is equal to this. Therefore, f satisfies the cross partial property on a simply connected domain. We have seen that the curl of a gradient is 0. What is the divergence of a gradient? If f is a function of two variables, then divergence of gradient of f, which is gradient dot gradient f, is equal to fxx plus f by y. We abbreviate this as double dot product. We abbreviate this double dot product as gradient square. This operator is called Laplace operator, and in the notation of Laplace's equation becomes gradient square f is equal to 0. Therefore, a harmonic function is a function that becomes zero after taking the divergence of a gradient. Similarly, if a function of three variables, f is a function of three variables, then you have this. Harmonic functions arise in many applications. For example, the potential function of an electrostatic field in a region of space has no static charge. There is no static charge is harmonic. Yeah, that was quite a lot. The curl part confuses me. Like I want the derivation of curl. I want to know why they're defining rotation like this. Okay, I will end the stream here then. And then next chapter I will start studying whatever the like next team I will start studying whatever the next chapter is. I will like read through this book and do some of the exercises once, and then I will like go more in depth with a more detailed book. Because I feel like this book does have some mistakes, like notation mistakes. Okay, I will end the stream here and then